All right, class, shall we try another one here? As you guys are getting closer and closer to the exam, let's try number 20, or from chapter 21, number 45. And as I read it here, it says a cylinder is closed at both ends. Okay, so maybe I have a cylinder. I'm going to put it on its side. It's closed at each end. Okay, so solid. Cylinder is closed at both ends and has insulating walls. Okay, so keep in mind then that heat energy can't go in or out. Okay. It's divided in two compartments by an adiabatic partition. So again, there's a partition. And again, adiabatic, meaning no heat can go through here. And remember, the outside also had the same thing. It said insulating walls. And so one of the things going on in my mind right now is that, okay, we cannot have heat flow in or out. And so whatever is going to happen here, this is going to be referred to as an adiabatic process. Compartments by an adiabatic partition that is perpendicular to the axis of the cylinder. Each compartment contains 1 mole. Okay, so 1 mole, 1 mole. Contains 1 mole of oxygen that behaves with a gamma of 7/5. So diatomic. Initially, the two compartments have equal volume, so there's some initial volume and some initial volume. And their temperature is, so we'll go 550 is the initial temperature of this, I'll call it compartment number 1 over here on the left, and 270 Kelvin for the initial temperature of compartment number 2. So same volume, same number of molecules, but with the left one at a higher temperature means it's going to be at a higher pressure. And so this partition is going to be able to slide over. It says the partition is then allowed to move slowly until it's balanced. That is, the pressures are equal. So as this moves over, the volume's going to change. It is going to be adiabatic, so there's going to be some final temperature to number 1 that goes down. It looks like this one moves over and squeezes number 2, so the final temperature of number 2, again, is unknown, although it goes up. So we know it's going to be greater than 250, and we know this right here is going to be less than 550. So it's going to go down in temperature. This is going to go up. And, of course, then there will be some final pressure that will equal each other. That's when the partition stops pushing. So final pressure number 1 equals to final pressure number 2 of the two chambers here. It says the partition is then allowed to slowly until the pressures are equal. Find the final temperatures of the two compartments. And you can use the result for number 43. Okay, so hopefully in this introduction here, you begin to see how this one's going to go down, this one's going to go up. They're not necessarily going to be at the same temperature. That doesn't matter. Energy can't flow across the partitions. The whole thing is insulated. They will never become the same temperature, but they push back and forth, and so what's going to become equal is the pressures. And we know before they move, the volumes are equal. Now, they give us 2 equations in number 43. Maybe I'll do the one in part B, because part B has to do with temperatures, whereas the part A has to do with pressures and volumes. But in part B, they say, show that the work during an adiabatic process is equal to NCV and then final temperature minus initial temperature. Now, the reason I jump on that one is because they are asking about final temperatures, and they gave initial temperatures. So I like that, although this is derived from the other equation they give in Part A. So I'm not sure which one's going to be better here. But I like this one because looking at this, and I guess this is the key to the problem, as chamber number 1 expands, there would be work. And I'll go work from gas number 1. And since the chamber is getting bigger, it would be doing work on the environment. That means the energy goes to the environment or the surroundings. And so the work would be leaving the gas. And so work for number 1 would be less than 0. And then likewise, it is then compressing number 2. So number 2 is being pushed on. So there's going to be some work here, and that's going to be greater than 0. And here's the best part is we know then that the magnitudes of the work would be the same, because that's where the energy goes. When number 1 expands, it compresses number 2. So the work being done on number 2 is coming from number 1. So the magnitudes of them, are the same. Maybe I should write it this way, that the work for number 1 is equal to negative of the work for number 2. Again, number 2 has work being done on it, so it's a positive number. If you take the opposite of that, that's where the energy came from. It came from number 1. So this would be a conservation of energy statement here. Okay. And then if I use this equation here, I could write something like this. NCV times the final temperature of chamber number 1 minus the initial temperature of chamber number 1 must be equal to, and then I'll put a negative, the work done on number 2. So this would be NCV, and the work for number 2 would be the final temperature of number 2 minus the initial temperature of number 2. And of course, I like this one because the NCVs cancel off. And you could even see here, this would be final temperature number 1 here. This side's going to have a negative final temperature number 2, which when I bring over is going to become plus final temperature number 2. Whereas over here, I have this initial temperature number 2, that negative and that negative make a positive. And then this one, initial temperature number 1, when I bring it over, it becomes a positive. And see, these two initial ones I know. The number 2 is the 250, and the number 1 is the 550. And so putting that together, it's 800 Kelvin. So I am, what I guess I'd say, halfway there in that statement, is I have decided or proven that the sum of the final temperatures of 1 and 2 have to be the same as 800 has to be the same as the sum of the initial temperatures of it. That kind of makes sense. That's the principle of conservation of energy. That's where we got this statement. Okay, and I say I'm halfway there because there's 2 unknowns, and I need 2 equations for that, and I just did one of them. But the other thing that's going on in my mind is the adiabatic stuff. So we know that PV raised to a gamma is equal to a constant. And I'm wondering then if that is enough information, the second piece of information that I need. And it seems like it will be, but you never really know till you keep tinkering here. So I'm going to put pressure volume to gamma equals pressure volume gamma. And if I apply this to chamber number 1, I guess this would be the initial pressure of number 1 and the initial volume of number 1 raised to a power of gamma. I'm not going to put a number 1 for initial volume because we did say that both chambers start with the same initial. So I'll just call it the initial volume. And then, of course, we're saying that pressure, or the chamber number 1 expands. Okay, so we're going to have a final pressure of number 2. And actually, let me just cross out I meant number 1. But even let me cross that out because we know that the final pressures, that was this statement, is going to be the same. That's when the partition stops getting pushed as the pressures even out. So this would be final pressure, and then this would be the final volume of number 1 raised to a power of gamma. So that got a little bit bigger. And let me apply the same equation, PV gamma, but this time let me do chamber number 2. So the initial pressure of number 2 times the initial volume of number 2, and there's no point in putting initial volume of 1 or of 2 since they're the same, okay, equals then the final pressure, and again, I guess this would be final pressure of number 2, but again, there's no point in saying final pressure number 2 versus number 1 because they are equal. I'll just put final pressure. And then this would be the final volume of number 2. And if we then move this second equation, the second adiabatic equation, to be under the first one here, we will get the initial pressure of number 1 times the initial volume raised to a factor of gamma, but then that's what this is going to be over here. The initial volume to a factor of gamma would cancel off, and so we're going to have then initial pressure of number 2. And so that's what happens when you take this one and divide it by that one because of the initial volumes. Okay, and then that has to equal what? And so this would be the final pressure over or times the volume of final number 1 to a gamma divided by that one, but it's again a final pressure. So the final pressure is going to end up canceling off, and we'll just get final volume number 2, and all of that is raised to a factor of gamma. Okay, and let me just double check that. So if I put that over to here, I get the ratio of the pressures, okay, and the initial volume goes away. Good. If I put that over here, the final pressures go away, and then we just have volume to a gamma. Now, here's where I could take this a step further. As I said, we really want this in terms of temperature because we do already have one equation with the 2 unknowns in it. We would like to find another one. So let's look at the initial conditions. Using the ideal gas law, the initial pressure of number 1 would be nRT initial over volume initial. And we could rewrite the initial pressure of number 2 as nRT initial. Initial number 2, initial number 1. Initial number 2 divided by lost my train of thought here. Oh yeah, divided by just like I did up here, the volume initial of number 2. But the N and the R are the same, and the initial volumes are the same. So this gives me a ratio of the initial temperature of number 1 over the initial temperature of number 2. And again, those numbers I know. The initial temperature of number 1 is 550, and the initial temperature of number 2 is 250. So that's what I would do with kind of these 2 steps. It's becoming the initial temperature of number 1 over the initial temperature of number 2. Now, the other side of this equation has to do with final volumes. Let me play the same little game here. How can I write the final volume? I guess this would be N and then R and temperature to the final temperature of number 1 divided by the pressure. And again, I can just put final. I don't need to put over number 1 or over number 2. Okay, so that right there is volume, final, number 1, to power of gamma. And then down here would be nRT final number 2 over final pressure. And again, raised to a power of gamma. And then again, notice the N and the R. Notice the final pressures drop away. And then so what we have is final temperature number 1 over final temperature number 2, each raised to a power of 1.40 for our diatomic gas. And that's perfect. This is our second half, right? See, our second half here is what's the relationship of the final temperatures. And so I would say now mathematically I have equation 1 and equation 2. Well, let me simplify this a little bit. Let me get to the ratio of final temperature number 1 over final temperature number 2. And I guess I'd get that by taking the 550 here and divide it by the 250. I would then raise that to get this by itself to the inverse of 1.4. So I'll go 1.4 inverse. And we are looking at a ratio of about 1.76 is kind of that ratio between those two. Okay, so if I then write it as 1.76 times final temperature number 2 equals final temperature number 1, and I put that back with equation I got at first, which is saying, okay, here is the substitute of final temperature number 1. It's 1.76 times final temperature number 2. Add to that final temperature number 2, and you get 800. Which, of course, when you add those, you get 2.76 times final temperature of number 2. So final temperature number 2 would be this 800 divided by 2.76, and we're looking about 290 Kelvin. So 290 Kelvin is the temperature final for chamber number 2. So chamber number 2 seems to warm up, as I said, right? We're going to compress it a little bit. So it warms up from 250 to 290. But keeping the 290 in mind and coming up to here, this would be then 800 minus the 290, and we're looking at final temperature number 1, again coming from here, as, what I say, 510 Kelvin. So again, when you add them, you get your 800 exactly. Yeah. And so that should be the 2 temperatures. So, yay, hope that worked well.